Okay, so hello everyone. I'm Manuel and I'm a PhD candidate at Stuttgart Media University and Ruhr University Bochum in Germany. And I'm presenting today my PhD topic, which is about applying program synthesis methods and adapting them to use them in game AI use cases. So, not working. So yeah, I can somehow. Okay, no. So yeah, my motivation behind this work is that most advances in deep learning are difficult to apply in real games due to their black box nature, and the lack of transparency and control makes them difficult to integrate them into games where player experience and narrative coherence are important, because unpredictable or inexplicable agent behavior can confuse players and frustrate developers. And how can we address this? And my plan to do this is with program synthesis, because programs are interpretable by design. They are controllable representations. You can adapt them and analyze them before using them in games or in real-world systems. So my goal of this research is to convert the logic of black box AI agents into symbolic programs that are readable, editable, and transferable to other domains in games or agents, or to learn the programs directly from the real world or from data. And if we have programs, we can answer questions like, why did the agent make that move? What concept is it using? Can I tweak its logic or for a new level or game mechanic? And what I did in my research was, 2 years ago, I presented an AIIDE poster here about explainability with programs. I adapted the Dreamcoder framework there for reinforcement learning environments based on imitation learning. And Dreamcoder is a program synthesis framework for neural guided search. And it also included a library learning module where programs are analyzed and then functions are extracted from these programs and added to the domain-specific language. So what you actually do there is learn a customized domain-specific language for each environment. And this domain-specific language should also then represent the concepts the agent has learned. And I tried this out on 3 different environments: on a simple maze running, maze navigation environment, and 2 miniature version of Atari games, which are with a symbolic representation. So all information is already in these environments, and I used asterisks and space invaders there. And in the bottom, we can see a program which Dreamcoder synthesized for the maze running agent. And on the right is like a snapshot of the library. And you can see there that the agent, in the first iteration, extracted a function to just check if 2 objects are equal. If the objects are equal, the agent will turn left and otherwise go forward. The next function which was extracted is like getting the position in front of the agent. And the third function, which is hierarchical and uses the first 2 functions, is function 15. And it calls like function 1 with a wall object. This actually means that if there is a wall in front of the agent, it turns left, otherwise it goes forward. And in a follow-up paper, I showed that this genetic programming is a better method for this because it's much faster and with a similar performance. So, and we also did a project with LLM-based program search, which is actually from the same Darkstuhl event where Mike and Em did their speedrunning paper. And there we did we tried out 5 different LLM providers. So in total 11 models on in total 29 tasks, where we had a big part of it was Python programs for agent control on the miniature version of Atari games, generating a Python function to generate mazes, like a PCG problem. And also we tried out 10 levels of BABA-SU if LLMs can interpret rules or destroy, create new rules. And we also used the tabletop games framework, and we had 12 games there where the LLMs needed to synthesize heuristics functions in Java in the tag framework. And then they were used in One Step Look Ahead or Monte Carlo tree search. And we did a round robin turnier over all these LLMs to find out which were the best ones. Then I also did 2 papers on logical programs. In the first one, I extended the few-shot Bayesian imitation learning framework for logical program policies from single agent reinforcement learning for simple grid-like games like NIM here to multi-agent reinforcement learning. And this was a simple cooperative environment where multiple players need to cooperate to pick up fruits. And what I actually showed there is that these programs could be used without retraining or finding new programs on larger grid sizes and also on multiple players. And the figure below was from my exact talk on Tuesday, which was about generating cognitive plausible explanations for board game agents. So in future work and conclusion, I still have some open research questions like how transferable are the program libraries between game environments and game agents? And a very interesting question would also be how scalable are these methods to more complex games or real-world applications? And I think that in future there's a lot of potential to use program synthesis for games as AI methods and hardware improve. Yeah. So yeah. Thank you. And I think